questions. Okay, let's write Math for Economists lecture. Probably 6, but I don't remember. Maybe 7. I will check when I will post.
Yeah, it seems to be the 6th one.
Okay, thank you. We have Friday. Okay, the recording I have. Everything is fine. So if you have any questions, just don't be shy. It's a perfect moment to ask your questions. In the beginning of every lecture, I will ask you whether you have some problems, some questions.
Yeah, I have one question. Because in our last lecture, we have an example about stories and graphs. It's super interesting. May we have some kind of examples if we have time?
I try to, I do my best to understand, but the channel maybe is a little bit noisy. Could you just type your
okay,
question?
I'm going to type it in our...
I'd like to answer your questions, but sometimes I just can't understand. Just please type it in the chat. I will read it and I will try to answer. Any other questions for the moment? I understood that it's something about graphs, but I haven't got exactly what is the main idea, what we should plot or graph. Last course, we have examples with story and graph. If we have time, could we have some more examples like this? So yes, we try. So yes, it's a natural idea to use graphs as much as possible. Yeah, I agree. Yeah, I will use graphs. Yeah. Okay, let's move on. Today we will start considering what is called linear programming. And we need funny stories. Oof, funny stories. Okay, I will try to provide some funny stories. Linear programming, once like a century ago, it was a fight between United States of America and Soviet Union about linear programming. It's a cool story because this technology nowadays, it's linear programming is used for high frequency trading, and who has got a fast, efficient algorithm for solving linear programming problems, at least approximately, but very fast. Then you can make money doing some high frequency trading, creating some high frequency trading robots and so on. But it's very useful topic in in optimization, because many problems may be approximately stated as linear problems. So many problems are not linear. Obviously, we have solved already a lot of nonlinear functions. But many problems can be approximated well with linear functions. And so if they can be approximated with linear functions, maybe this linear function will have, I don't know, if you are optimizing a big portfolio, it may contain 1,000 of shares, of different shares, so that there may be 1,000 of variables to optimize over. And that's maybe if you are doing high frequency trading and you need to rebalance your portfolio, reacting to changes that arrive every 10 milliseconds, then you have to elaborate efficient, fast algorithm to solve that kinds of problems. We will not speak about very efficient algorithm. We will just discuss what is linear programming, and we will solve some problems by hand. Maybe I will show you at least something using notebooks on computer, but basically we will not delve into very modern, very efficient linear programming algorithms, but at least some basic ideas how to solve linear programming problems and what it is. Okay. So I will start with the example, because when I start with the example, it's maybe with a book, how to avoid visiting this lecture and maybe 2 or 3 future lectures. If you just like to have some fun and to go outside to play snow and so on, you may just read Ferguson. I think it's called, I don't remember how it's called, just a moment. I remember that it's Ferguson, but the book is like linear programming concise introduction, or concise introduction. So if you'd like to just avoid my lecture, then you can just read Thomas Ferguson. Thomas Ferguson has a very, very great style. At my opinion, it's one of the clearest style of exposition for mathematical books. So it's really very easy to read. So that's a very good style. I'd like to have a exposition style like that. And basically, I think we will cover chapters 1 up to 4 and maybe 5, something like that. Okay, let's move on. Let's start with the example. Linear programming, basically, it's a particular case of optimization with inequality constraint. So from first point of view, it's just a particular case of what we have already done. So imagine 2 examples, example A and example B. I will start with 2 examples at once. I will have 2 problems, minimization and maximization problem. So the first problem will be to maximize x1 plus x2 subject to non-negativity constraints. X1 is greater than 0, x2 is greater than 0, and some inequality constraints that will be also linear. Linear programming is not about computers, but is about optimization with linear function and linear constraints. And my constraints will be x1 plus 2x2 is not greater than 4. 4x1 plus 2x2 is not greater than 12. Minus x1 plus x2 is not greater than 1. And I will have a problem that at first we will just use the same numbers, but will be at first glance completely different. But it will turn out that the second problem is very related. The link between these 2 problems will be very strong, very important for the development of the theory. It's this link is used in many modern machine learning methods like support vector machines. It's called duality, and this duality will be used in many mathematical models. But at first, I will just use the same numbers for completely different problem. So my problem will be minimize 4y1 plus 12y2 plus 1y3 subject to non-negativity constraints. and two inequality constraints. 1y1 plus 4y2 minus 1y3 will be greater than 1. Sorry, it's 1. And 2y1 plus 2y2 plus 1y3 will be greater than 1. So I have stated two problems. And now we will discuss how to solve them and what is the link between them. My main question is how to solve them. How to solve them. And second question, what is the deep link? What is the link between these two problems?
Excuse me, am I right that it is our constraint after x bigger than 0, there is x1 plus 2x2. Is it constraint or what?
Yeah. All these are constraints.
Okay,
but
thank
I
you.
have all these are constraints. I have just stated non-negativity constraints a little bit higher, but yeah, all these are constraints. All they are equally important to us. This line, this blank line, is just to separate non-negativity constraints from more difficult constraints. But basically, yes, all these are constraints we need to use. Okay, first question. My first idea is my first advice: always, if you are not required to use Lagrange multiplier methods and first order conditions for inequality constraint, if you are not required, then try to avoid optimization with Lagrangian function. Try to use graphical methods as much as possible. So my the first answer is to use graphical approach if possible. If it's not possible, for example, it would be difficult to use the graphical approach for the second problem because I have three variables. For three variables, I need to draw in 3 dimensions, and it's a little bit it's not so obvious how to draw in 3 dimensions. Yeah, we may, but if I will have 4 variables, it will be tough. So let's start with the first problem, and then we will discover the link between two problems. Maybe you may, even now, you may see some, you may think that it's just a coincidence that I have, so look, we have a similarity between problems. I have 4, 12, 1, and this is 4, 12, 1. I have 1 and 1, and I have 1 and 1. And I have, if I look at the columns of the first problem, the coefficients are 1, 4, and -1. If I look at the rows of the second problem, I will read the same numbers, 1, 4, and -1. If I look, so it's like the rows of the first problems are the columns of the second problem. And it happens that the link is very deep and it's used in other optimization algorithms. This link is exploited and it's very important. Okay, so let's solve the first problem when we can use a graphical approach. It's a very good idea to use graphical approach if possible. And if it's not possible, then we may use first order condition for inequality constraint, and then first order conditions for inequality constraints. We already have studied them extensively. Okay, so for the moment, I will focus on the graphical solution of the first problem. Okay? The problem is clear? We have to
let's go.
Yeah, let's move on. Sorry, my screen is very small. It's much smaller than a normal standard whiteboard, so I'm a little bit obliged to switch my screen often, and I understand that it's not so easy to follow when I have a lot of equations, a lot of inequalities, but I'm trying to do my best. If you have any advices, what I can do, I'm open to your proposals. I have asked at the end of the previous lecture who is for Python notebooks on Google Colab, and who is for handwritten written notes. And the biggest part was indifferent. So many of you voted that this is the same for me. And I think there were only 10 or 9 students who were not indifferent, but the biggest part of those who were not indifferent, they voted for handwritten notes. So I will mainly use handwritten notes, but sometimes I think I will prefer online notebooks to show you some code used for optimization. Okay, we go on.
Yeah, okay. And actually, for this screen is better because I think most of our students use screenshot. If they want to review something, they just can look at the screenshot. So it's better than more than a whiteboard or blackboard. It's still the same.
Oh, maybe, but on the whiteboard you can make a photo.
Oh, yeah.
Okay. Okay, I will just make a small copy, maximize x1 plus x2, x1 is greater than 0, x2 is greater than 0, x1 plus 2x2 is less than 4, 4x1 plus 2x2 is less than 12, minus x1 plus x2 is less than 1. Okay, so my first idea is to use graphical approach as much as possible. If I have 2 variables, I don't care about this Lagrangian function. I can just solve the problem graphically. Okay, both x1 and x2 are non-negative, so I work on in the first quadrant of R2 in the positive quarter of my plane. Then I will draw all these inequalities. So x1 is 4, x2 is 2. So this is the first line. This is the first line. And as x1 plus 2x2 is less than 4, then I should choose the part of the plane that is that contains the point 0, 0. We may check which part of the plane we need just by checking 0, 0 point, whether the inequality is satisfied at 0, 0, or the inequality is not satisfied at 0, 0. Okay, let's consider the second line. We have x1 is 3. It's 3 here and 2, 6 there. That is the second inequality. And once again, I should choose the part of the plane that contains the point 0, 0. And finally, I have the third line. The third line is minus x1 plus x2 equal to 1. And I think this line will go something like that, and will be minus 1, 1. And the third line will go like this. And once again, I should choose, I check whether 0, 0 belongs to the inequality. 0, 0, 0 minus 0 plus 0 is less than 1. The inequality is satisfied. So I choose the part of the plane that contains 0, 0. And finally, I have my set D. This is the set D. This is the region D on the plot. And I draw level curves of the objective function. So my objective function is easy, is linear, is x1 plus x2 is my objective function. So I will draw it using red color. If I consider the sets x1 plus x2 equal to some constant c, these sets are called level curves. In my particular example, level curves will be linear. They will be just straight lines. And these straight lines are like that. So this is a line. This is x1 plus x2 equal to some c. That is, I move on my line. Oops, the distance between level curves in my scenario should be constant. Should be like that. Maybe one passing through that point. And so on. Okay, these are level curves. I see that C grows in the right north direction. So x1 plus x2 grows in the gradient point to the right, to the east-north direction. And if I'm obliged to choose a point in the region D, so I'm choosing a point in the region D, so I'm maximizing my x1 plus x2 given x1, x2 belongs to the set D. And what is the obvious solution in my case? What is the best point, the biggest C, the biggest value of C in the region, in the black region D?
The intersection?
Yeah.
Level curve and the...
Yeah, exactly.
Region.
The best point in my, when you have a simple two variable problems, two variables problem, then it's just easy. You just draw the inequality, you draw the level curves of objective function for linear programming problem. Everything will be just a straight line. Will have no parabolas, no sine, no cosine, just straight lines, a lot of straight lines. And this is the obvious point, optimal point. And in optimal point, we see from the plot that constraint 1 is active. Constraint, so this is 1, this is 3, this is constraint 2, this is constraint 1, this is constraint 3. So the second constraint is active or non-active, and the third constraint is which constraints are active?
The second is active, the third is inactive.
Yeah, I completely agree that the second is active and the third is non-active, inactive. Okay, yeah, active means equality. So I just see that x1 plus, I will just copy, I will have 2 plus 2x2 is just 4. The second is active, 4x1 plus 2x2 is 12. And the third one is non-active. That means that minus x1 plus x2 is strictly less than 1. I have 2 active constraints and 1 non-active constraint. And I can easily find x1 and x2. So I just solve this small system of equations. I will divide the second equation by 2, obviously, or I may just subtract one from other. So I will have 8 equals to 3x1, yeah, and it's like that. And I have x1 optimal is 8 over 3, and x2 optimal is 4 minus 8 over 3 divided by 2, and it will give me 2 minus 4 over 3, and it is 2 over 3, as if I'm not mistaken. Okay?
Okay.
Yes, clear.
Excuse me, could you please show all the picture? So
Yeah.
why do we assume that this point is the maximum? For example, why not the intersection of line constraint 3 line and constraint 1 line? Because I mean, it's obvious, but how can we be sure, like 100%?
Oh, I don't understand your question. If it's obvious, then you are sure.
Как бы, это по рисунку очевидно, но это же, по идее, мы не строго доказали.
Or no, the proof is so.
I can say something.
So my answer is following. You are right in the sense that our plot is not exact; it's only sketch. But what is required from a good sketch? From a good sketch, so obviously it's not an exact plot. If you look carefully at my line, oh, it's a curved line. It's not a straight line, obviously. The plot is not perfect. You're right. But it is, I think, I don't remember who provided this definition of geometry, that geometry is an art of exact arguments based on a wrong picture. So when we are using a picture, we are using qualitative, we are using it qualitatively. I'm not using it in a quantitative matter. Oh, look, I will just take a ruler and I will measure this distance. I will measure this distance using a centimeter, and I will write it in the answer. That will be obviously a wrong approach. So my idea is that we are using only qualitative properties of our sketch. We are not using it just to measure using centimeter. The idea is to use features of the sketch that are stable and that are not influenced by a by our imperfections. So yes, the plot is not perfect, but I'm basing my arguments on features of the plot that are not affected by imperfections of my plot. Yes, my plot is not perfect. The lines are not straight. You can see that my red lines are not exactly parallel. They are not straight lines. But what is the qualitative? From the important point, I see that what is the slope of this function? The slope of red line, or maybe I should write it in red. the slope of this line is equal to -1. And the slope of that line, slope of this line is -2, okay? Do you agree?
Okay, so if, for example, if we provide the solution in the exam, it's okay.
That's perfect.
Okay.
Yeah, that's perfect.
Thank you.
But if your plot is on your plot, it's not clear that the slope of red line is you cannot compare, or the comparison is wrong, of two slopes. So it's very important that the slope of the red line is -1 and it's less by absolute value than the slope of the black line, number 2. Yeah, that's very important. That's a qualitative feature on the plot. And so it's important to have the exact, the right inequality between slopes. That's important. But the exact slope is not important. Yeah, the qualitative features are important, and quantitative features are not important on the sketch. So my 4 is not twice as big as my 2 on the plot. That's okay. This segment is not exactly equal to twice the segment from 0 to 2 on the vertical axis. That's okay. But the comparison of the slopes is important. So yeah, I think it's a good idea that geometry is the art of exact conclusions based on a wrong picture. Okay, let's move on. We have found our solution. Let's find the maximal value. The maximal value of objective function is x1 star plus x2 star, and it's 8/3 plus 2/3, and it's 10/3. Okay, we have found the maximum point. We have found the maximal value. So, woohoo, we have finished our solution. Now, let's move on to the second problem, and let's discuss the link between the first problem and the second problem, okay? So now we will solve the second problem, and we will see that they are intrinsically related.
Okay, yeah, thank you.
Okay, I will separate my screen in two, and I will have, let's call them problem A and the problem B. Problem A, once again, I will copy it.
Excuse me, can you return back for a moment, please? I'm sorry.
Yeah.
Thank you very much.
Okay, we may go on.
Yeah, thank you.
Okay, let's go on. We maximize x1. So I'm just copying my problems. So if the problems are already copied, then just wait a little bit, because I need them on the screen to discuss them. Basically, I'm just doing a monkey job. I'm just copying the problem. And non-negativity constraint, x is greater than 0, and minimize 4y1 plus 12y2 plus 1y3, y are greater than 0, 1y1 plus 4y2 minus 1y3 is greater than 1, and 2y1 plus 2y2 plus 1y3 is greater than 1. Okay, so let's write first order conditions for two problems. So let's write first order conditions. So I will write Lagrangian function for two problems, and I will write first order conditions for two problems. Okay.
Okay.
So let's write Lagrangian function. Let's start with this problem. We have discussed that when we have a special case of non-negativity constraint, we have two options. Either we can include them in Lagrangian function, either we can exclude them from Lagrangian function. And in these two cases, first order conditions will be equivalent, but will be a little bit different. Yeah, we have two options. Do you remember that we have discussed a simplified version of Lagrangian function, parsimonious version without non-negativity constraints and changes in first order condition implied by this emission. Anyone remembers?
Yeah, I remember part of them.
At least who remembers that we have discussed it? I'm not asking about the first order conditions for this parsimonious Lagrangian function, but just who remembers that we have discussed this topic?
Yeah, I remember.
Okay.
And we have
And-
similar questions in the last course.
Okay,
is it
so-
called Kuhn-Tucker conditions or something like that?
Kuhn-Tucker condition, yeah. So sometimes the general Kuhn-Tucker first order condition, it's called, they are both called Kuhn-Tucker conditions. So alas, their name is not, yes, but both first order conditions are sometimes called Kuhn-Tucker conditions. So, and the parsimonious one and the full one, they are or sometimes called Kuhn-Tucker conditions. Yes, you are right, but that gives us no hints how to remember them or how to. So we have we have proven the parsimonious version given the full version is true. We haven't proven yet the full version. We will prove it a little bit later. My strategy is just to provide they start with providing the means how to solve the problem, and then at the end we will discuss some proofs. Proofs are maybe tough. That's okay. Proofs are not. The understanding of proofs is useful, but they are not directly required for the external exam. And obviously, when you try to understand the proof, you develop your skills in mathematics, but these proofs are not directly required for external exam. So I will postpone them to the last but one lecture. Okay, so we have proven parsimonious conditions, assuming that the full Kuhn-Tucker first order conditions are true. Okay, let's use the parsimonious version. So I will introduce Lagrange multipliers lambda 1, lambda 2, lambda 3 here. And so my Lagrangian function will be x1 plus x2 plus lambda 1 times 4 minus x1 minus 2x2 plus lambda 2 times 12 minus minus 4x1 minus 2x2 plus lambda 3 times 1 minus x1 plus x2. Yeah, that's okay. The parsimonious version of
super awesome.
Parsimonious version of Lagrangian function. And let's write first order conditions. Parsimonious version that is used, this version of first order condition is used when you have non-negativity constraints. Okay, first we may copy all original constraints. So first, x1 is greater than 0, x2 is greater than 0. Then we have original constraints. X1 plus 2x2 is less than 4, 4x1 plus 2x2 is less than 12, minus x1 plus x2 is less than 1. What else? Who can tell me what other constraints do I have in first order conditions?
Производная по x, одному первому, по x второму.
Yeah, dl with respect to dx should be 0, positive, negative.
Equal to 0.
No, we have a
Less or equal than 0.
Yeah, you are right that in a full version, the derivative with respect to dl to dx, one should be 0 in full version. But if I have removed my non-negativity constraints from explicitly copying them and introducing 2 more lambdas, lambda 4 and lambda 5, if I'm using all the inequalities, even non-negativity constraints in my Lagrangian function, then you are right, dl dx should be 0. But in my case, dl dx1 should be less than 0, okay, or equal to 0. Yeah, that's okay. We have proven that. I don't remember 1 or 2 lectures ago. What is dl with respect to dx2? What is the first? So I have
Excuse me.
spoiled it. Yeah.
Could you please explain once again why is it not equal to 0 but less or equal?
Ooh, okay, I will do it quickly. So let's. So why? So if you have a parsimonious, so there's a parsimonious version of Lagrangian function. If you will have a full version of Lagrangian function, it will be x1 plus x2 plus blah 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 blah. It will be the same plus. You will have to introduce lambda 4 times x1 plus lambda 5 times x2. Do you agree with me that in a full version of Lagrangian function, you will have 2 more terms?
Yes, definitely.
Okay, and if you write dl full with respect to dx1, it will be dl parsimonious with respect to dx1 plus you will have lambda 4 and you will have equality to 0. Yeah.
Yes.
But you know that in the first order conditions, lambda 4 is non-negative. So dl parsimonious with respect to dx1 is non-positive.
Okay. Thank you.
I will not do with full version. I need a parsimonious version. So I will work with that, but that's a motivation why, not a motivation, it's a honest proof. Yeah, it's a proof. It's not a motivation, but it's an explanation why dl parsimonious with respect to dx1 is not equal to 0, but equal or less than 0. Okay, as we have mentioned already, lambda 1, lambda 2, lambda 3 are non-negative.
Boris Borisovich, I'm sorry, can you scroll a bit up for a second?
Yeah. What's wrong?
Yeah. I just was rewriting. Thank you.
Yeah, with a big whiteboard, it would be much better. You obviously you can take screenshots, but a lot of screenshots is worse than one board with a lot of formulas seen simultaneously.
Excuse me, actually, there is a solution for this because there is some kind of online board. So you can share a link with us and you write on the board. If they want to have the hologram of the board, they can look at the website.
I have seen some. Yeah, if you have a specific advice, just send me the link. I will look at them. Okay, so what are other first order conditions? Who remembers what are the other first order conditions? Oh, we have already done this many times. Lambda
Well,
one.
lambda times dl over dx equal
lambda
1 equals
times
0.
dl d lambda 1 is 0. Lambda 2 times dl d lambda 2 is 0. Lambda 3 times dl d lambda 3 is 0. x1 times dl times dx1 is 0. x2 times dl dx2 is 0. And these original inequalities, they can be written like dl with respect to d lambda 1 is positive, dl with respect to d lambda 2 is non-negative, and dl with respect to d lambda 3 non-negative. These are all first order constraints. Okay? Any questions?
No, it's clear. Thank you.
Okay, let's move on to the second problem, the problem B. The problem B. Let's write L parsimonious for the problem B. I have many ways to write it. I may transform all my, I may transform into maximization problem, but let's write it directly and let's just carefully look at the sign of every derivative. So I will use the following way. I will just write it like it is, just write it and just think about every sign, just a possible strategy. So there is one strategy that is easy to remember, that just always transform a problem to maximization problem with inequalities like boom, 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 greater or equal than 0. Or there is another strategy that I will follow now. I will just write my Lagrangian function as it is, and I will think carefully about the sign of each derivative. Okay, just I will write it like this. For y, let's call the Lagrange multipliers, I will call not lambdas, but I will call them mu. It will be mu1 and mu2. So I will just use different names for Lagrange multipliers. So it will be 4y1 plus 4y2, plus 12y2 plus 1y3 plus mu1 times times what? Times 1 minus 1y1 plus 4y2 minus 1y3 plus mu2 times 1 minus 2y1 plus 2y2 plus 1y3. Okay, now let's stop for a moment and let us observe the miracle. If you look carefully at these two Lagrangian functions, the Lagrangian function for the first problem and the Lagrangian function for the second problem, you can just look carefully, 10 seconds, 20 seconds, and just say, oops, it's the same function. Who has seen this miracle? Who has who has a vision? Who has the vision that the third eye to see that this is the same Lagrangian function?
Sorry, I'm trying, but I do not know the answer.
Okay, let us look carefully and see the corresponding terms in each function. I have 4 lambda 1. I have 4y1. I have 12y2. I have 12 lambda 2. I have 1 lambda 3. I have 1y3. I have 1x1. I have 1 mu1. I have 1x2. I have 1 mu2. I have minus x1 times lambda. Minus x1 times lambda. I have minus mu1 times y1. I have, let's say, let's look at this term, minus 4x1 lambda 2, minus 4y2 mu1. Do you see that it's just the same function, but with different names for the variables? The same function, just names are different. Yeah?
Yeah, now it's clear.
So completely the same function, but the names are different. Let's look at the correspondence. X corresponds to mu, and lambda corresponds to
y.
y. Okay, so these two problems are intrinsically related. The x is a, you look at the problem A and you see, oh, x1 and x2 are variables, but x1 and x2 are Lagrange multipliers for the problem B. If you look at the problem B, y1, y2, y3 are original variables. But if you move to the problem A and you just rename Lagrange multipliers, not as lambda 1, lambda 2, lambda 3, you may name them like y1, y2, y3. So if you just rename these into y1, y2, y3, you rename these mu1 and mu2 like x1 and x2. And if you just choose different names of Lagrange multipliers, then you will have exactly the same Lagrangian function. Let's go on. Let's look that first order conditions will be, you can guess probably that first order conditions will be exactly the same. So let's move on to the first order conditions. Y1 should be non-negative, Y2 should be non-negative, Y3 should be non-negative. That is the original requirement. And mu1 is non-negative, mu2 is non-negative. This is a requirement of the standard first order condition in inequality optimization. Look, this line exactly corresponds to that line. So not only Lagrangian functions are the same, the first requirement that lambdas, multipliers, and original variables should be non-negative. In the first order condition for problem A, original variables and Lagrange multipliers are non-negative. In the problem B, original variables and Lagrange multipliers are non-negative. So that's the same. That's the same, that's just different notation. Okay, let's move on. These equations are exactly symmetric. So you will have an exact copy y1 times dl dy1 should be 0, y2 times dl to dy2 should be 0, y3 times dl dy3 should be 0. The complementary slackness conditions for mu1 times dl d mu1 is 0, mu2 times dl d mu2 is 0. So these conditions are exactly matched. Okay, just the naming of the variables is different. Okay, we go on.
Yeah.
Just let us look at original constraints. Original constraints. What are the original constraints? Original constraints is dl with respect to d mu, this value should be less than 0. Yeah. So let us look at this dl d mu. This is dl d mu, and dl d mu should be less than 0 because I have written them like that. 1 minus left-hand side should be less or equal to 0. So I have original constraint like dl d mu 1 is less than 0 and dl d mu 2 is less than 0. This is exactly like in the first order condition of problem A. Okay, we go on.
Yeah, let's go.
And finally, we need to find dl with respect to dy1. If I'm writing a maximization problem, then the derivative should be less or equal than 0. But I have a minimization problem. So I should invert the sign once. And if I invert the sign once, I will have a constraint that this derivative is greater or equal than 0. And the same thing for y2 and the same thing for y3. And basically, I see that not only the Lagrangian function is the same up to renaming of variable, but I also see that first order conditions are the same. These two problems, problem A and problem B, are related. That we see that it's just the same problem, but with the renaming of variables. And now I can easily solve the problem B. Okay, so what we have seen? We have seen that first order conditions are the same up to renaming of variables. The Lagrangian function is the same up to renaming of variables. And so basically, if I have solved the first problem, I have solved the second problem. Okay, so let's obtain the solution of the second problem very fast. Yeah, are you ready?
Yeah, sure.
Okay, what about the solution? So what we have seen? We have seen the miracle problem A and problem B are just the same, up to renaming. You just need to call mu is x, lambda is y, and bingo, you have the solution of the other problem. So now let's solve the problem B. We know that the solution of the problem A is the following. X1 star was, as far as I remember, it was 4/3 or 8. Who remembers what is the value of X1 star, X2 star?
8/3, if I'm not mistaken.
8/3, and X2 star was
2/3.
2/3. Okay, but these are original variables in problem A, and these are Lagrangian multipliers in problem B. Okay, these are Lagrangian multipliers for problem B. Okay, they are original variables for problem A, but they are Lagrange multipliers for problem B. If Lagrange multiplier is positive, the constraint is active or non-active?
It will be non-negative.
No. If the Lagrange multiplier,
if non-zero, it is active.
Yeah. If I look at these two inequalities, mu is x, mu1 is x1, mu2 is x2. This is the same problem up to renaming of variables. So I see that mu1 is 8/3, mu2 is 2/3. Okay, because mu is x, is just renaming of variables. Okay, that means that constraint 1 is active, constraint 2 is active. So I can deduce that dl d mu is 0, dl d mu2 is also 0. Okay.
Okay.
So now let's move on. So this is problem A, and this is problem B. So x1 star, I will copy all the results. Mu1 is 8/3, dl d mu1 is 0. X2 star is 2/3, that mu2 is 2/3, dl d mu2 is 0, because in first order condition we should have mu times dl d mu is 0. And finally, I have two equations. Yeah, I have what are these two equations? These two equations are what is dl with respect to d mu is 1 times y1 plus 4 times y2 plus, sorry, minus 1 times y3 is 1. And the second equality is 2y1 plus 2y2 plus y3 is 1, because that means if dl d mu is 0, so that means constraint number 1 is active and constraint number 2 is active. Okay.
Okay.
How many equations do we need more to solve finally the problem? How many equations do I need?
One more?
Yeah, I need one more equation because for the moment I have 3 unknowns and I have 2 equations. So basically one more equation and I'm happy. Okay, let's look. Everything okay for the moment? Because I will go back to the plot.
Yeah.
Yeah, I will go back to the plot for 10 seconds and I will have one more equation, and it's important to look at the plot. Let's go back to the equation, to this plot. We have seen that at our optimal point, first constraint is active, second constraint is active, the third one is non-active. But in first order condition, we should have something like lambda times dl d lambda should be equal to 0. Lambda times dl d lambda should be equal to 0. Lambda times dl d lambda should be equal to 0. In first order condition, we have equations like that. That means that dl with respect to d lambda 1 is 0. That means dl with respect to d lambda 2 is 0. But that constraint means that dl with respect to d lambda 3 is I forgot how I have included it. I think I have included that with plus. Yeah. No, it's greater than 0. Yeah, that's okay.
Yeah, okay.
So what I conclude, if an equation is non-active, constraint is non-active, what I can conclude about lambda 3?
It's 0.
It's 0. But who is lambda 3 for the problem B?
Y3.
Yeah, it's Y3. Constraint number 3 is non-active. Lambda 3 is 0. But if you go in the dual problem, then you will have Y3 is 0. Basically, we have finished. So now I have Y3 is 0. Why Y3 is 0? Because Y is just renaming of lambda in the problem A. Original variables for problem B are Lagrange multipliers for problem A. Lagrange multipliers for problem A are original variables for problem B. And so basically, I'm just solving y1 plus 4y2 equals to 1. 2y1 plus 2y2 is equal to 1. I think I will just simplify the second equation. Y1 plus y2 will be 1 over 2. I will subtract them, and I will have 3y2 is 1 over 2, y2 is 1 over 6, and y1 is 2 over 6. Yeah, I think like that. Okay, so finally, the answer for the second, for the problem B, y1 is 1 over 6, y2, sorry, y1 is 2 over 6, y2 is 1 over 6, y3 is 0, and that is the answer for the second problem. Okay? Any questions?
Yeah, super.
And it is the minimizer, right?
Yeah, it's a minimizer. Yeah, exactly. What was a maximizer in the problem A is a minimizer for problem B. Yeah, exactly. You're right.
For example, can we change the signature in these functions like y1 change it with y2, or that means y3 must be non-active?
I don't see your point. What can we do?
For example, on the last page's paragraph, you will change the place for y1 and y2 and rename it.
Yeah.
Then the y3, which is not active, still the same function.
And what is the question? I don't see.
Sorry, I'm going to type it in.
Okay. Okay. So what is the advantage of the method of the link we have discovered? We have already discovered a good method. So some like final remarks for current lecture. Final remark. It's a bad idea to remain y3 to y1. No, so if you can rename variables, but you should do that with some goal in mind. Obviously, you can remain y3 to y1, y2 to y3. You can remain them, but that will not introduce you any new insight. So you can rename them, but if you just rename, you just change the order of equations and like that. Final remark. If I have a problem like two variables, 5 constraints, then I can use graph. And I can use graph. If I have two variables, I can just x1, x2, draw some figure and find optimal point and say, woohoo, I have found optimal point. And now the miracle. I have a problem with two constraints, and 7 variables. I have 2 constraints and 7 variables, y1, y2, y7.
Why not 5?
The way you may have 5. You may have 5 constraints. It's not important.
Oh, okay.
My idea is that at first, it seems that it's impossible to solve this problem graphically. How will I solve a problem with 5 variables graphically? Well, I cannot draw in 5 dimensions. I'm a poor 3-dimensional human. I can draw in 5 dimensions, not to say in 7 dimensions. So, but the trick, right now we have a trick. Just rename the variables. So we just do the trick. We go from a problem to, we will like inverse the problem. We will have a dual problem. We will transform it into 5 constraints. 5 constraints. 2 variables. So now we have a trick that allows us to go from 2 constraints and 5 variables. We have a trick to go to 5 constraints and 2 variables.
Excuse me, is it always possible? Because like here, the constants were good, but is it always possible?
Yeah, it's always possible. Yeah, it's always possible to, or in linear case at least, or approximately in non-linear case, it's always possible to switch the number of equations and variables. And if you have a problem with 2 constraints and 5 variables, the tricks, we will do it next time once more, and we will provide some general theorems, but the trick is already at our hands. We can interchange the number of variables and the number of constraints, and this problem, we can solve graphically. And we just need to say, oh, these 2 variables were Lagrange multipliers for original problem, and these 5 new Lagrange multipliers were just original variables for original problem. So this is trick to switch the number of Lagrange multipliers and the number of original variables. That trick may be used to solve new problems graphically. That's a final idea of the lecture, that we have a trick to switch the number of constraints and the number of variables. And it's always possible in a linear case, and non-linear case may be in real life problems approximated. Obviously, it's done with computers, not with hands, but real life problems of optimization of portfolio with big number of shares can be approximated by linear programming, and it's done like this in real life. That's all for today. See you next time. If you have any questions, just don't be shy, write me. That's all.
Sorry, could we just wait for a minute? I have a question. I'm typing on the chat.
Okay.
Thank you very much. Have a nice evening. Goodbye.
Excuse me, I have one question. Can you please answer? So this trick, do we have some conditions for this trick to be applicable, or?
Linear functions, non-negativity constraint. You can always, so the trick, if you look, we will discuss and we will do it next time, but basically, what is the trick? You just transform columns into rows, and basically that's the whole trick.
I see.
Needed?
So they need to be linear and non-negative, right?
Yeah.
Non-negative in what sense? Because I can see minus x1.
Non-negative, I mean constraint. X should be non-negative because it will be, so the condition that is non-negative. And even even when you have no such constraints, so even there is a trick to work without these constraints, because if you have, so even this is not important, because that duality is very powerful. For example, you have no constraints like that. You have a variable that can take arbitrary values. Imagine that x2 is non-negative, but x1 can take arbitrary values. So I will represent x1 like x1a minus x1b, and I will introduce x1a is greater than 0, x1b is greater than 0, and everything will be non-negative, but x1 will take arbitrary values, and I will use this trick. So even this condition with smarter tricks can be ignored, but that's not the topic. So the short answer for your question is just we have a linear function and linear restrictions and non-negativity constraint.
Thank you very much. Now it's clear.
And the trick, basically, you transform maximum to minimum, you transform columns to rows, and whoop, you are done. Okay, one more question in chat. X power 5 functions could not find exact solutions. Is it connect to final definitions in last page? No, we work with linear functions only. We are not solving cubic equations here or x power 5. No, this trick is used for linear functions and linear constraints.
I have a question. That means there is a distance between linear functions, linear constraints, and normal functions. So what makes them separate?
What makes them
Separate. Yeah.
Simplicity. They are too simple. We have no the graph is just roughly a polygon. So basically, this makes them separate. They are simple.
Yeah. Another small issue is today, all the functions in our discussion could draw a graph. At least it could be representing our graph. But it's not means all the functions could have a clue or have a line which draw on graph, but these functions still exist. How do we deal with such kind of functions?
No, I don't understand your question. Sorry.
Yeah, we'll try it on chat.
Okay.
This is the next one.
Boris Borisovich, could you please scroll a bit up? Like where you were showing the derivatives of the constraints. Which ones were active and which ones were not?
Okay. It's somewhere. Yeah. Yeah.
Yeah, exactly. Thank you.
Yeah, actually, my question is based on this graph.
Today, functions all could draw on graphs. If the function could not show or graph, how to deal with these situations? The answer is when you work with, so it depends whether you're asking about real-life optimization or whether you are speaking about exam. If you are on the exam, then if you cannot draw the graph, then you can just solve first-order conditions for Lagrangian problem if you are on the exam. If you speak about the real life, then computer algorithms like gradient descent or method of momentum or Adam optimizer. So if you speak about exam, then you just write Lagrangian function, write first order conditions without plotting if the graph is not feasible. If you work with real-life optimization problem, then you just use some numeric procedure like gradient descent or stochastic gradient descent algorithm.
Thank you.
Okay, any more questions?
Yeah, there is a one in the chat. I'm typing.
Okay. Oh, I don't see why will you have different answers. If the extremum is unique, then I don't see your point. Yes, in real life optimization, when you have a very tricky function, computer numeric algorithms may indeed fail to find the extrema. Yeah, that may be so. Many gradient descent or stochastic gradient descent algorithms in real life, they will stick to some local extrema without finding global extrema. That may happen. In real life, yeah, sometimes it's tough to find the extremum of some complex maximum likelihood function. That's, yeah, you are right. In real life, it's harder to find an extrema, and the numeric algorithms may fail to do so. But if you speak about exam problem, If you have a external exam problem on optimization, there will be there may be many optima, but if you just write first order conditions, if you just honestly will solve them without error, then you will find them. I don't see your point. We'll have different answers. I don't understand. So if you have a simple optimization problem, it has a solution. Maybe there are many points of extremum, but maybe there are no points of extremum, but the answer does not depend on the way you are solving it. I don't see a point. With some cases, use Lagrangian function will have local max, but do not use sometimes no local max. Maybe you can provide some examples of problems. Write me a letter, but
Yeah, okay.
I don't see your point.
Yeah, okay.
If in non-degenerate constraint qualification conditions are satisfied, then Lagrangian function will find all the suspicious critical points, and you need just to check second order conditions.
Yeah, okay.
Okay, bye-bye.
Thank you, Boris. Bye-bye. We love you. Nice day. Have a good weekend.
Bye-bye.